So in the previous two videos, we have discussed what is geometrical isomerism, what is cis-trans isomerism, and what is the EZ system of geometrical isomerism. And now in this video, we will be discussing the conformational isomerism. Now the reason for geometrical isomerism was that across the carbon-carbon double bond, rotation was restricted or hindered because without breaking one bond out of the two, that is, we needed to break the pi bond so that the rotation can occur. Okay, now because of this restricted rotation across the carbon-carbon double bond, the molecule was able to exist in two forms. Okay, now in case of conformational isomerism, what is the reason for conformational isomerism is the rotation across carbon-carbon single bond is free. So we said that if one nail is there, it can be rotated. Okay, so now because of this free rotation across carbon-carbon single bond, a number of spatial arrangements are possible, which are known as the conformational isomers. And the phenomena is known as conformational isomerism. So let us now move into it. Sharing my screen with you. All right. So we are now doing the conformational isomerism. Conformational isomerism. So you can write here the different arrangements of atoms in space which can be obtained, the different arrangement of atoms in space which can be obtained due to rotation about carbon-carbon single bond are called conformations. Conformations. And this phenomena is known as conformational isomerism. Phenomena is known as conformational isomerism. So we have already discussed that when a carbon-carbon single bond is formed, there is sp3 hybridization of the carbon. So this carbon is sp3 hybridized, this carbon is also sp3 hybridized. So there is a single bond between these two carbon atoms, and the rotation across this single bond is possible. Now this will lead to different kinds of arrangements. Now, if we say that the rotation across carbon-carbon single bond is completely free, it is not the case. It is not completely free. There is some energy barrier, because for rotation also we will be needing some energy, and that energy barrier is 1 to 20 kilojoule per mole. Depending upon the nature of molecule, this energy barrier can be 1 to 20 kilojoule per mole, which is a very small barrier, and it can be overcome at ordinary temperatures. So this is the reason why rotation across carbon-carbon single bond is free. It is not completely free. Energy barrier is there. Okay. Now, before moving into the conformational isomerism, taking the example of it, we will be discussing the ways to represent conformational isomers or conformations. Ways to express or represent, ways to represent conformations. Conformations. All right. Now we have two ways. You can just draw a line in between. So one is sawhorse representation, and the second one is Newman projection. Newman projection. Sawhorse representation and Newman projection. Now, in this case, in case of sawhorse representation, what we do is carbon-carbon bond is viewed from an oblique angle. Carbon-carbon bond is viewed from an oblique angle, and the various bonds, are represented by lines. So suppose we have to represent the conformations of ethane, CH3. Now it is having carbon-carbon single bond. So we will be presenting it like this. And the 3 hydrogen atoms attached to it will be represented by lines. So this is the rear carbon on upper right hand side. This is the front carbon on lower left hand side. Now I'm coming back on my screen so that I can explain it to you how to visualize this carbon-carbon bond. Now again, suppose these are 2 carbon atoms, right? Now what we will do, we will be looking at it in an oblique angle like this. Okay, now this is my right hand side, this is my left hand side. So the front carbon, it has to be kept on the left hand side. It will be like this. Okay, and the rear carbon, it will be kept on the right hand side. So it is the upper side, it is the lower side, lower left hand side, this is the upper left hand side. So this is the position of the 2 carbon atoms which we are visualizing. So this is in case of sawhorse representation. Okay, now the 3 bonds, hydrogen bonds, they will be represented by lines. So we can consider this is a pen and it is the bond, CH bond, which is represented by this pen, that is the line. Okay, now let us move into the Newman projection. So in case of Newman projection, what we will do is, we will be presenting the 2 carbon atoms in the form of 2 circles. 2 carbon atoms are represented in the form of 2 circles, one behind the other. Okay, now if we will look at the front carbon, I think I should first show it to you, then we will be writing it so that you can understand it better. Okay, now we are considering the 2 carbon atoms in the form of a circle. The front carbon atom will be presented by a point, a dot. Now just consider this is the carbon atom. Okay, now this is the back carbon atom, and if you consider this is the front carbon atom, this is the bond, and this is the front carbon atom. So you will be able to see only a dot. It is imagination. Okay, you need to imagine it that this is the front carbon atom. We will be presenting it like a dot in the center of the circle, and this circle is presenting the back carbon atom. Okay, now the hydrogens which are attached to the front carbon atom, they will be shown starting from the center, that I will show in the diagram. And for the back carbon atom, the hydrogens, carbon hydrogen bonds, they will be presented as from the circumference of this circle, Okay, so let us now move to the whiteboard. I'm so sorry, just a sec. Okay, so this is the whiteboard. Okay, now we are discussing the Newman projection. So in this, what we will do is, we will be considering that the front carbon is a dot and the back carbon is a circle. This is the dot. Now the hydrogens which are attached to the front carbon, they will be presented like this. And the hydrogens which are attached to the rear carbon, they will be shown from this position. That is from the circumference. The bond angle here is, we already know it is 120 degree. All right. So these are the two representations of the conformations or the conformational isomers. That is the Sawhorse representation and Newman projection. Now we will be moving into the conformations of ethane. Just clearing my screen. Conformations of ethane. Conformations of ethane. Now what we say is the rotation across carbon-carbon single bond is free. Okay, now suppose we are considering this Newman projection in which the hydrogen atoms are situated this way. That is, they are at the maximum possible distance from each other. The hydrogen atoms of the front carbon and hydrogen atoms of the back carbon, they are at maximum possible distance from each other. So this is one form of ethane. The second form of ethane is in which the two carbons are situated in a way that the hydrogen atoms of the two carbon atoms are very close to each other. So now what will happen? When the hydrogens are very close to each other, their bonds will be very close to each other. This means the electrons which are involved in the bond formation will also be very close to each other. Now, when similar charges are close to each other, there will be repulsive forces. There will be repulsive forces. So in this case, when we have this arrangement, there are more repulsive forces. Here we have lesser repulsive forces. Now always keep it in mind that whenever there is large repulsive force, there is large energy of the molecule, there is lesser stability. More repulsion, more energy of the molecule, lesser stability. Lesser stability. Now, a number of conformations are possible in case of ethane, but energetically only two are important. Energetically, only two conformations are important in case of ethane. All right. Now, these two conformations are known as eclipsed conformations and staggered conformations. Just clearing my screen. These two conformations are, number one is eclipsed conformation. Number two is staggered conformation. Staggered conformation. Now, what is eclipsed conformation? In eclipsed conformation, the hydrogens of one carbon are directly behind the hydrogens of other carbon. Hydrogens of one carbon are directly behind the hydrogens of other carbon. Okay, now the bond pairs of carbon-hydrogen bonds are very close to each other. Consequently, there will be high repulsive force. Now, this repulsive force makes it less stable. So this is the Newman projection. Now, if you want to draw the sawhorse representation, it will be like this. All right. Now, this is having greater repulsion. So greater energy and lesser stability. Now, in this case, in the staggered conformation, the case is like this. The hydrogens of one carbon atom are not just behind the hydrogens of other carbon atom, but they are at the maximum possible distance. They are at the maximum possible distance, and this arrangement is known as the staggered arrangement. That is, the hydrogen atoms of the two carbon atoms are staggered with respect to each other. They are staggered with respect to each other. So this angle is 120 degree. If we see the angle between the hydrogens of two different carbons, it is 60 degree. Now, if we rotate the carbon-carbon single bond, we keep one carbon fixed at its position and we keep rotating the other carbon atom, what will happen? It will keep changing from eclipsed form to staggered form and from staggered form to eclipsed form. So now what is the angle at which we need to rotate? We need to rotate at the angle of 60 degree. If we rotate eclipsed form at the angle of 60 degree, it will give us the staggered form. And if staggered form is rotated at the angle of 60 degree, it will give us back the eclipsed form. Okay, so we can draw that figure now. We will be showing the rotation across carbon-carbon single bond. So here is the eclipsed form, which is less stable. Eclipsed. Now we are rotating at 60 degree. One carbon is fixed. Suppose we are keeping the front carbon fixed, right? Now, if the front carbon is fixed, the position of hydrogens will also be fixed and back carbon is rotated. So now this angle is 60 degree. Again, we are rotating it at angle of 60 degree. So it will again lead to the formation of eclipsed conformation. So this is staggered. Again, eclipsed. Now, how to know the relative stability of the eclipsed and staggered conformations? Now, we have already discussed that in case of eclipsed conformation, there will be more repulsive interactions because the hydrogen atoms of the two carbon atoms are just behind each other. One behind the other is there. So repulsive interactions are more, higher energy is there, lesser stability is going to be there. Now, in case of staggered, the hydrogen atoms are at maximum possible distance from each other, lesser energy, higher stability. Okay, now just write down. The carbon hydrogen electron clouds are at maximum possible distance in staggered conformation. Maximum possible distance in staggered conformation, but they are very close in case of eclipsed conformation. The repulsive interactions between electron clouds which affect the stability of conformation is known as torsional strain. Torsional strain. So what is torsional strain? It is the repulsive interactions between the electron clouds. So these are the bonds. They are having electrons. They are forming electron clouds. Okay, now if there is repulsion, that repulsive force is known as the torsional strain. And the magnitude of torsional strain depends upon the angle of rotation. So how much is the torsional strain? If I suppose I rotate only up to 30 degree. If I rotate only up to 30 degree, this will be something like this. If I rotate this to 30 degree, something of this kind will be formed. Hydrogen, hydrogen, hydrogen. This is the front carbon. Almost approximately we can say this, there will be the position. This will be the position of the hydrogens of other carbon. Now again, here will be more torsional strain than in case of staggered conformation. So this means the torsional strain, it depends upon the angle of rotation about the carbon-carbon single bond. And this angle is known as dihedral angle or torsional angle. Dihedral angle or torsional angle. Now we can draw the energy level diagram for the different types of conformations possible in case of ethane. Energy level diagram for different conformations possible in case of ethane. So you can just draw it like this. Here we have energy. So we have already studied that staggered conformation is stable and it is having a lower energy than eclipsed conformation. So here you can draw the staggered conformation. Now here will be the, at the highest level, there will be eclipsed conformation. So you can draw here the eclipsed conformation. Again, here will be the staggered conformation. Here we have staggered conformation. So on this side, it is angle of rotation. Angle of rotation. So here it is 60 degree. Here again we have rotated it at 60 degrees. So here it will be 120 degree. All right. Now, if you need to tell what is the energy barrier here, the energy barrier in case of rotation across the carbon-carbon single bond for ethane, it is 12.5 kilojoule per mole. Now, this energy is very easily available even at ordinary temperatures. So even at ordinary temperatures, the two forms of ethane, they will keep on interconverting. That is, eclipsed form will get converted into staggered and staggered will get converted into eclipsed conformation. I hope this is clear to you. Just stopping to share my screen, coming back on screen. Okay, so these are the conformations of ethane molecule. Now in the next video, I will be taking up the conformations in case of propane molecule and in case of butane molecule. So it will be very easy for you to understand these now. So let us move to the next video.